All right, similar again, a box on a ramp, yet another box on yet another ramp. It's initially at rest. And now, for some reason, they don't really have to, but they're saying the positive direction of the x-axis is up the plane. And I would say, well, I would have figured that out because I know all about how to select coordinate systems. But they are saying they are making this stipulation. And so they're saying the positive x-axis is up the plane, which is fine. You don't need that assistance. You can figure that out by yourself based on the criteria, based on the coordinate system selection criteria. All right. So here's a question. We know all about this system. And now the question is, what is the frictional force on the box from the plane when P equals this value? Okay. So let me just start. I'm going to start with number one. This is a job for force analysis method. Okay. And we have all of the force analysis method recipe items. There's the free body diagram. There's the coordinate systems. It's only one body. There's decomposition. There's the inventories. And then there's the acceleration statement. And then there's crunching. So this really should be familiar to you. All right, so this is a job for FAM, which means, now let's see. I have friction, so I'm not able to ignore friction. And the part A says, what is F sub S? So my dollar sign is, the dollar sign is friction. So now here's the question. Friction is the dollar sign, friction force. Friction force is the dollar sign. So now my question is, when I read that, it says, what is the frictional force acting on the block from the plane? So I'm saying, well, if they're asking me to find out the friction force, are they talking about kinetic friction or are they talking about static friction? And the answer is, I don't know. So I'm going to read through the question again. It says, this force P, which is right here visually, is acting on a box weighing 48 newtons. The block is initially at rest. So that's noteworthy, I suppose. Maybe. It's initially at rest. I know theta. Positive X is up the plane. So I took care of that. And now they are giving me the coefficient of static friction and the coefficient of kinetic friction. And they want to find out this frictional force. So again, I'm going to repeat my question. Does this mean I need to find F sub K or F sub S when P is negative 5.1 newtons I hat? All right, so let's see, number 3. I have a question. Does, or I'll say is the combination, combo for short, is the combo of P, that P force indicated visually, and mgx enough to overcome static friction? And static friction is written as F underscore S question mark. So I need to do sort of a situational test here. And before I get too far ahead of myself, here's the free body diagram. So let's do the whole free body diagram thing. We're getting really good at this. I have weight going, that's a little bit too thick. I have weight going straight down, acting on the center of mass. There's weight. This is my P force. I'll just redraw it again. This is my P force, my externally applied P force. And at this point, this is weight mg, W equals mg. This is the P force right here. I'm just going to overdraw that again, reinforce it. Weight is a vector. All right. So I'm not going to draw friction because, to be honest, what kind of friction do I have? And what kind of friction I have is going to be based on the combination of the P force and mgx. And here's mgx. I keep saying mgx, and you should know this by now. You should see that when I break things into components, that's the y component, and this is the x component. So we've seen this a lot. You know that this is mg y, and you know that this is mgx. And let me erase this, maybe just clean this up a tad bit. And the hypotenuse there is mg. So we've seen this a lot of times, and you're just seeing it one more time. But now I have to do like a means test. And I'm going to read this sort of reflective question one more time. Is the combination of P, which is right here, P, and mgx, which is right here, those are both down ramp forces. Are they enough to overcome static friction? So that's my first test. And I'll say, I'm having this dialogue with myself, and I would say, well, what is F subscript S? And then the answer to that is F subscript S. Static friction is this stickiness factor, mu sub S. This is the coefficient of static friction. Once again, a sheet of rubber is much stickier than a sheet of ice. So rubber has a much higher coefficient of static friction. And there's a lot of stuff I'm leaving out that's just quite honestly available to you in the lecture video. So just another plug times F sub N. That's the answer. That's how much static friction I have generally. Specifically, here's how much static friction I have. I have mu sub S times the normal force, which is mg cos theta. We've seen that. And I guess technically speaking, if I wanted to be airtight, I would maybe do a 5a and do a y force inventory, saying that the sum of all y forces is I have the normal force going up and mgy going down equals mass times acceleration. And this would be y. And my acceleration statement is a sub y equals 0, since the box doesn't leave the ramp, since there is no plus or minus y motion. Okay. So then we're saying 5c F sub n equals mgy, which is mg cos theta. So I've done this a lot of times. I was sort of tempted just to skip and say, well, we've done this so many times, but that seems a little bit cavalier. So there's 5a, b, and c, 6, got it. So here's how much static friction we can cough up. Ready, set, go. F sub s equals mu subscript s, which for me is given 0.510. Mu sub s is 0.510. There's no units there. Times mg. I don't know m, but I do know mg. Mg is the weight, and weight is given as 48 newtons. Yes. Cosine of theta is cosine of 18 degrees. So if I need it, my static friction can provide up to 0.51 times 48 times cosine of 18. I can cough up. My static friction can scale up. Static friction will increase or decrease to be whatever it needs to be and nothing more. So if needed, I can get 23.28 newtons of static friction. That's good to know. And let me say this again, static, and this is in the lecture video. Static friction can be greater than or equal to 0 or less than or equal to mu sub s F sub n. So it's kind of tricky. Static friction scales, meaning if you don't need it, if it's not needed to keep things motionless, it will be 0. If you need it to grow to a certain point to maintain a static situation, it will grow. It will keep growing until it can't grow anymore. And at that point, you've exceeded its threshold. All right. So then, okay. What is the combination? What is the combination of mgx, which is trying to pull the box down, and what is the combination of mgx and p? And this will tell me, is this box going to move or is it not going to move? So here's the combination: mgx plus p, mgx plus p. And these, again, what I'm drawing here in step 10, these are the downward oriented forces that are trying to drag the box down. Static friction is trying to resist those. Static friction is trying to counteract those. So here's mgx. Mgx is mg sine theta plus p. So let's just keep going with that. This equals mg 48 newtons times sine of 18 degrees plus p, and p for part A is 5.1 newtons. They gave you p in unit vector form, 5.1 newtons. So right here, let's talk about this just for a second. They said this externally applied p force is negative 5.1 newtons in the I hat direction. And that's right here. That's what I'm drawing right here. This for part A, this is p equals negative 5.10 newtons in the I hat direction, or negative x direction. All right, so this is how much downward force is acting on this box. I have 48 times sine of 18 plus 5.1. I have 19.93. So I win. Static friction wins. So, aha, big moment. F sub S wins. Okay, so you know what it means. Because this is a great story to tell. Fascinating too. I can cough up, if needed, I can cough up 23.28 newtons of static friction. But for part A, I only need 19.93 newtons of friction, because once again, this 19.3, this is the down ramp. This is down ramp force. So I just need to recap. I have shown that these two forces, mgx is a down ramp force, P is a down ramp force. They combine to exert 19.93 newtons of downward force on the ramp. And the good news is, from a static friction point of view, I can meet that. So number 11. Okay. Success. F sub S, in this case, equals 19.93 newtons. That's the answer to part A. And again, just so it's not clear, or just so I'm being confusing. No, I mean to say static friction can grow to be as great as 23.28 newtons. It doesn't need to grow to that point. It just needs to grow to 19.93 newtons, because if static friction is 19.93 newtons, everything remains motionless, which is the criteria. All right, let's move on, because now we have a different P force. What happens if you crank up the force? So basically you're saying, I'm getting impatient. I want to move this box down the ramp. So now part B, step 12, part B is saying, what if you increase? What if P, this down ramp force, is now 8.4 newtons down the ramp like that? Everything stays the same. So we can kind of fast track this now, not cut corners. Okay. I still, F sub S can, once again, provide up to 23.28 newtons of up the ramp force. That's the max. That is what the static friction force can scale to provide of up ramp force. Okay. What's the down ramp force? What now is the down ramp force? And the answer is still the sum of those two vectors. It's still going to be mgx. Mgx is a downward force. So is P. That's a downward force. And with numbers now, I have mg sine theta plus P, or mg is 48 times sine of theta, and theta is 18 degrees, plus P, but P has grown. P has now grown to be an 8.4 Newton force. So numerically, what I have now is 48 times sine of 18 plus 8.4. Right, so now this is my total downward force, 23.23 newtons. So step 16, I guess I'll go here.
Do you mean to use cosine, or are you supposed to be using sine?
You tell me. What should I be using? If my goal is to capture mgx, what do I do? So what do you do to express mgx using this triangle? Do I use sine or cosine or tangent?
Yeah.
And just to play it out, just because this is good reinforcement, I would say, well, if this is the angle theta, and these two are, and I know this might be a little hard to read, but maybe not. I know this. I know sine of theta equals side opposite, which is mgx, over hypotenuse, which is mg. And that's how I'm saying mgx equals mg sine theta. Okay, so I have this much downward force. So the question is, can the static friction force scale to meet or to offset this 23.23 Newton down ramp force?
Hey, Professor, can you just move your screen down just a little bit?
Yeah. And hopefully this isn't too small to read. Okay.
No, that's perfect. Yeah.
Okay. All right. So there it is. So 17. Great success. Again, for you Borat fans, great success. F sub S does indeed offset this force, this down ramp force. And I've already shown that. All right, so the answer is F sub S equals 23.23. So again, this is the sort of the trickiness or the challenge with static friction. Static friction is scalable. It grows only to what it needs to be to keep everything motionless until you exceed its limits. And then here's the ultimate example. We go to a toboggan hill on Hines Drive. I'm sitting on a toboggan, and it's snowy, it's snow-covered ground. You push me, and you know from experience, It takes a lot of force to start me moving because you have to overcome all of that static friction. But you know this from experience. Once you get me moving, you can kind of back off. It takes a lot less force to keep me moving at a constant speed than it does to get me to move to begin with. And that's exactly what's going on here. Static friction will keep me motionless until you basically punch through. And then once you punch through static friction, then you're encountering kinetic friction. So this is the answer to part B. Done with part B. Yes. Where did I say done with part A? Well, we're done with part B. Okay, this was part A. All right. Let's do part C. Same thing again. Everything's the same, except you are getting increasingly impatient. Step 18 says for part C, now this P force that you're applying equals negative 15.4 newtons. So it's going to be the same chain reaction of Q and A. How much downward force do we have? Here's the amount of downward force. So maybe I'll just say F down. The total down ramp force equals mgx plus P for the umpteenth time. And we know mgx is mg sine theta plus P. So with numbers, here's the downward force, F down equals mg, which is 48 newtons times sine of 18 degrees plus P, and P has now grown to 15.4 newtons. So here's the total amount of downward force. 48 times sine of 18 plus 15.4, 30.23. So that's it. Finally, we have defeated static friction, 30.23 newtons. That is the total downward force. So F sub S is finally defeated. So that means the box moves. Box moves down the ramp. So if the box is moving down the ramp, the friction it encounters now is kinetic friction. The friction exerted on the box as it's now moving down the ramp is kinetic friction, is F sub K, not F sub S. All right, so because this question is saying what's F sub K, because the question says what's the friction force? What's the friction force in this situation, in the part C situation? The friction force is F sub K, because again, the box is moving. There's no more static friction. There's kinetic friction. F sub K equals the stickiness factor, mu, like mu2, subscript K for kinetic, coefficient of kinetic friction times F sub N. And we know that F sub N is mg cos theta. That's the answer. And again, just over here, just one more triangle game. If cosine of theta equals side adjacent is mgy over hypotenuse. This is how I'm getting mg cos theta for F sub N. Okay, so now just plug in numbers and you'll be done with part C, 23. I've got mu sub K, which is 0.34. There's no units, times mg, which is 48 newtons, times cosine of 18 degrees. And this is the friction force, which happens to be kinetic friction. 0.34 times 48 times cosine of 18, 15 and some change, 15.52. Okay, newtons. That's the answer to part C. So these problems, these are good. I mean, don't be misled, you guys. I am taking far more time than it would take you to do this, but that's just because I'm taking this opportunity to really drill down into some basics, some commentary. All right, good problem.